So we proved that if V and W are two vector spaces for the same field, say F, and if home V W denotes the set of all vector space homomorphisms of V into W, then this home VW is also vector space over F. We have further proved that V and W are finite dimensional. In that case, home VW is also finite dimensional. And in particular, the relationship between the dimensions of VW and home VW also we proved to be that the dimension of home VW is the product of the dimension of V over F and the dimension of W over F. In particular, we obtained a basis for home VW. And if you recall, how did we obtain the basis? So we took a basis, say B1 for V, B2 for W. And since B1 is a basis for V over F, say consisting of vectors V1, V2, Vm, and you can write that this is a linear combination of these VIs, and these coefficients are, which are also called as coordinates of V with respect to the ordered basis, say V1, say alpha 1, alpha 2, alpha n, then these in fact are uniquely determined for a given V. Once these are uniquely determined, then we can define the map. So we define the maps Tij for all I1 to n and for all j1 to m. These maps were defined for V, which is the unique linear combination, say alpha IVI, I varying 1 to 10. Tij of V as alpha IWJ. And in particular, this acts on the basis vectors, so say V1 as follows, that also we have proved. So this for the basis vectors, say Vk, so Tij of Vk, now this is 0 if I and k are different, and Tij of Vk in case I and k are same is equal to Wj. This is what we proved. So recall the particular case, AB and W are same. In that case, home VV is also finite dimensional if V is finite dimensional, and the dimension of home VV will be m square if the dimension of V over F is m. One particular case which is of very much importance in itself is when W is the field F. So this can be treated as a vector space over itself. So W is F and F is of course the field. So in that case, the dimension of W over F will be 1. And what do we get is that this is the dimension of V over F now is m times 1, and that is simply m, that means the dimension of V over F. So this is called the dual space of V. So dual space of V is so the dual space of V over F is denoted by, so we shall be denoting by putting this as V hat. So this V hat is nothing but we know that this is V W, and W is now F. And we know that if the dimension of V over F is m, in that case, the dimension of V hat over F is also same as M. And if it's finite dimensional, V hat is finite dimensional, and both V and V hat have the same dimensions. This is what we have proved. We in fact proved more as the basis also we had obtained. So now this basis for V hat. The elements here, one more thing is that the elements of V hat are called linear functionals. So what is a linear functional? The linear functional is a vector space homomorphism from V2 so, and we shall denote this by say V hat. So if V hat is in V hat, what does it mean? That this V hat is a homomorphism from V into F of V into F. So V goes to, you can say that this image of this is say V under say V hat, like that. So V hat is a map and V is a vector. If you want, you can put here U or W so that you don't get confused. So this is how that it takes the elements of V to an element of F. So this V hat under V, or you can put W if you want, that you don't confuse. So now this is a scalar. This is a scalar. This is an element of F. Now, in particular, let us take V be finite dimensional. So if dimension of V over F is say M, with the basis let us say B1 or B if you want, say V1, V2 and Vn, let us say this is the basis. Now, so we had takes every element of V into a scalar in F. In particular, we had also will take the vectors here from the basis to this. So recall the TIJ maps, how the TIJs are there. So recall the TIJ maps. So they were V to W and V, if this was the linear combination alpha I Vi, I1 to N, going to V of Tij as alpha IWJ. Now here you can see that these where Wj where B2, the W1, W2, Wm is the basis for W over F. All right. So in particular, this recall that this Vk of Tij. So in particular, Vk of Tij. So This is in case I is equal to k. So this becomes your Wj and 0 when I is not equal to k. This is what it is. Now you can see that this the if W is equal to F, then dimension of this is 1, and B2 can be taken as any set consisting of just one element, any singleton set, say alpha, and alpha is in F, and this is not 0. So in particular, if we take, so we prefer the standard basis. The standard basis means we can take this for W over F. So J is just 1, and this is for all. So this means that your the dimension is here M, the dimension of W over F. So the basis has just one element. Call it W1. Say W1 is 1, and there is no other element. So Vk of Tij, so we need not to write this J, therefore because this is 1. So Vk of Tij, this is simply Wj and this is W1. Now this is when I is equal to k, and I is equal to k, and 0 when I is not equal to k. I. Now, since j is 1, so this j is 1, so this is I1. Now, there is no point in writing this 1 every time when this is not there. So, we drop this also. So, we simply will write that Vk of Ti. This is now W1 is 1. If I is equal to k and is 0, if I is not equal to k. That means Vk of Ti is simply delta Ik. That means this is 1 if I is equal to k, and is 0 if I is different from k. So this is actually is the Vi hat. So denote this Ti by Vi hat for every I 1 to n. So what we have got is that corresponding to the basis vectors, hence corresponding to a basis, and we can also fix the order. So ordered basis, say B, V1, V2, and say Vn for V over F, there is a basis for V hat over F, namely V hat. So V hat is to denote these vectors V1, V2, and this is Vn hat. Where we know that Vi hat is an element here. So it's V to F, and that takes each V to V under Vi hat. And particularly, so Vk will go to Vk of Vi hat, and this is delta Ik. And this is for all I, 1, n, and for all k, and for all k, 1 to n. So corresponding to an ordered basis B, we have a basis here for home V F, which is called the dual space V hat. And this basis, so since this is a basis for the dual space, so this basis is called the dual basis for V over F with respect to the ordered basis V for V over F. So we have got a dual basis for V hat over F. And how is it defined? It's defined as V1 hat, V2 hat, Vn hat. The image of every basis vector Vk of V over F is Vk under Vi hat is delta Ik. Where delta Ik is the Kronecker delta. That means this is equal to 1 when I and k are equal, and is 0 when they are distinct. So we have got a basis. So you can see here that Vi hat under Vi will be 1. So Vi under Vi hat is 1. And V1 is not 0 since this is a V1 or each Vi is a basis vector. Is a basis vector. So Vi is not 0. So here is a vector which is not 0, but its image is 0. So what we have, in fact, we can rewrite also as for a finite dimensional vector space and for a non-zero vector V, there is an element Fv not equal to 0. So hence for a finite dimensional vector space over F, for a non-zero vector V in V, There exists now an element here, say f in v hat. Instead of writing v hat, we shall prefer to write this so such that now v under v hat. So you can call v hat if you think say v hat such that v under v hat. This is not zero. Or instead of writing the elements as v hat of v, since they are functionals, so they give a scalar value, and therefore it's advisable that we must denote this by say f, g, h, and so on. So we prefer denote the elements of v hat by say f, g, h, and so on. The way we define the functions. In any case, if v is also f, then this is a linear functional from f to f, or say for example f is r, so this becomes simply a function, real valued function. And if v is say r2 or r, in that case this is the function of variables. Function of two variables means the domain is r2, but the range is r. So when this v is rn over r and f is r, in that case the linear functionals are also called functions of several variables or multivariate functions. But here we have arbitrary field, and therefore in that case we call them as linear functionals. So what is a linear functional? Linear functional is the vector space homomorphism of V into the field F. The elements, so therefore we shall now prefer to call as F, G, H, and so on, instead of V hat, U hat, W hat. So what we have got is that for a finite dimensional vector space, say V over F, say vector space V over F, or a non-zero vector in V, there exists a linear functional, say F, in V hat, such that this V under F is not zero. The other thing is that, of course, there is no harm if we continue writing like this VF, but since the word function is derived from functional is derived from the word function, and it is customary to write functions as fx for the image of x under f, gx for the image of x under g, and so on. So instead of writing this as vf, we shall also prefer to write vf as fv. So we shall be writing fv instead of v. All right. Okay, so now what is f? So f is here is a linear functional. So f is a map from v to f, and v goes to, now we shall be writing this as f F is linear. It's a homomorphism. So it preserves sum. So f of v1 plus v2 is same as f v1 plus f v2, and f of alpha v is alpha times f v. And also you can recall that corresponding to every vector, say v, we have defined this as v hat, and this v hat, now we are writing this as f. So this element defines a functional here. So this is fv. So given so for every v, there is here under f, this is fv naught. Now let us take v naught in v is a fixed element and allow f to vary over v hat. Allow f to vary over v hat. So f, g, h like that. Now corresponding to this, we shall have fv naught, gv naught, and so on. So v naught is fixed. Then fv naught, this defines a linear functional on v hat into f. Then fv naught, this defines a linear functional of v hat. So what is happening that and how this fv naught is defined by, say, this is instead of calling this as fv naught, so this fv naught, if you want to write, you can write as the map. This is tv naught. So the map is from your let us say v hat to f. So f goes to f of v naught. Fv naught is a scalar. So for a fixed v naught and varying f, so f goes to fv naught, then g going to gv naught. So all of them are scalars. So let us call this map which is taking every element f. So this f is taken. So call this say tv naught. So tv naught we are defining as a mapping from v hat to f, and this tv naught. So tv naught is a map we are defining that takes every f in v hat. The image here, this is the image. So this is what? This is tv naught of f. So what is the image? Image is fv naught. And this is a scalar because f is a linear function. So this tv naught is a map which takes every linear functional f to fv naught. So gv go to gv naught, h will go to hv naught, and so on and so forth. So tv naught is a map from v hat to f. What one can prove is that, in fact, this is a linear functional. That means this is a homomorphism. So this you can prove. So what is to be proved? That tv naught of PV naught is a homomorphism over F from where to where? From V hat. So this is from V hat to F. Which is actually V hat hat. The homomorphisms of V hat to F, and therefore in our notation this is V hat hat, or is called V double hat. This is the dual, and this is called the second dual. Space of V over F. Now, for proving that this is a homomorphism, what you need to prove is that TV naught of F plus G, that it preserves the sum, and also TV naught of alpha F, that it preserves the scalar multiplication. Now, this TV naught of F plus G, how have we defined the TV naught of F as F of V naught? So, this is simply is F plus G under V naught. Now, F and G, they are homomorphisms. And the sum of two homomorphisms, if you remember, it has been defined that this is F of V naught plus G of V naught. The T1 plus T2 acting on V, T1V plus T2V. So this is because of this. Now this is same as, so this is TV naught of F plus TV naught of G. And that is for every F and G. In V. And now for every alpha in F, TV naught of alpha F, so this is alpha F of V naught. Now F is a homomorphism, and alpha F is also homomorphism. And how it is defined, that alpha T acting on V, alpha times V under T. So this is F V naught. So this is for every alpha in F and for every F and G in V hat. So this TV naught, the map, it preserves addition, it preserves the scalar multiplication, and therefore TV naught is a homomorphism from V hat into F. So what we have got? So we have got now a vector space, namely here, which is in V hat hat. So this is called the second dual of the vector space V over F. And one more word about the dimensions. So if the dimension of V over F is M, then we know that the dimension of V hat over F is also M. And you apply this same again, this is true for every vector space. And hence, the dimension of V hat hat, which is the second dual, is same as the dimension of V hat over F, is same as the dimension of V over F, that is M. So as many times you take the duals, the dimension is going to remain same. Just 1 second. So let me recall what we have just now proved. That given a vector space mu n, we can obtain its dual. Dual means this is home VF, so it consists of vector space homomorphisms from V into F, and in case of V being finite dimensional, this dual is also finite dimensional. Also that the dimensions are same in case of being finite dimensional. Now, since V hat is also a vector space, we can think of its dual, and this dual, which is now the dual of V, is called second dual. And once again, if it is finite dimensional, the dimension of the second dual and the dimension of dual and the dimension of the vector space V over F, all of them are equal. So this is what we have got. We also know that two vector spaces, say V and W, over the same field, say F, then they are isomorphic. In fact, they are isomorphic if and only if their dimensions are same. So recall for finite dimensional vector spaces, say V over F and W over F, that V is isomorphic onto W if and only if their dimensions are same. So dimension of V over F is same as the dimension of W over. They are same. So here it's quite natural that hence if dimension of V over F, say M, is finite, then V and V hat have to be isomorphic because they are of same dimension. And again, this is isomorphic to the second dual. So that gives that V and V second dual are also isomorphic. We can obtain a mapping also particularly. This mapping was psi. So we can obtain an isomorphism. So let us define psi, and this psi is taking a V to, let us say, V hat hat. So what are the elements here? The elements here, so this is V, and V under psi, this is an element of V hat hat. So what is V hat hat? Home V hat F. So that means this is a mapping. This is a mapping from V hat to F. So this is a mapping, therefore, from V hat to F. And this domain of V psi, which is a mapping, is therefore V hat. So it has to take F under V, and this is psi. And this has to be a scalar. This has to be a scalar. Now recall that if we denote this V psi to be the way we have been defining this TV. So this If you take that this V psi is so this sends to this. So if we denote this V psi by, let us say, TV, then V goes to this. So psi is a mapping from V to V hat hat. V goes to, this is V of psi. V of psi is TV. TV is from here V hat to F. F is sent to F of TV. We preferred to write this as TV of F. Okay. So this we claim that this will be now TV of F is, if you remember, this is F of V. Now this is a scalar. So you can prove that this is actually is an isomorphism. So what we claim is that this psi is an isomorphism of V onto V hat hat. So that means you have to prove that psi preserves the sum and psi preserves. Now for that psi is a homomorphism, number one. Psi is a homomorphism since it preserves the sum. Since for every, let us take, where is psi? Psi is from V to V hat hat. So psi preserves the sum. So V and W, if you take two elements V and alpha in F, so V and W under psi. How we are defining V and W under psi? That is an element here. This is TVF. So this is the T of. So this is the mapping T of V plus W. So this is T of V plus W, and this is a map. This is a map from V F. How it is defined that F goes to, this is T of V plus W F. And what is this? V plus W under FV, no? Under F. And this is FV plus FW. FV is TVF. This is TVF. This is TWF. So that TVF, you can see here that this is the basic. So that makes this. So this T of V plus WF is equal to your TVF plus TWF. And that is for every F. And that is for every F in V hat. So that means TV plus W. This is a homomorphism that you can prove. So what we have proved that TV plus W of F is TV plus TWF, And this is simply your giving. So this is TV plus TW under F. T of V plus W under F. And this is for every F in V hat. So as maps, this is T of V plus W is same as TV plus TW. And that makes that makes that V plus W under psi is same as V under psi plus W under psi. So it preserves this sum. And likewise, you can prove that alpha so psi preserves this sum. Same way, you can prove similarly for every alpha in F and every V in V, psi preserves the scalar multiplication. That means alpha V of psi is same in alpha V under psi. So recall that for every U psi is a map from V hat to V. So recall that this V psi is the map TV, is a map from V hat to F, and that takes V2. So this takes this TV of F is defined as F of V. F is from V hat. So alpha V therefore here of psi, alpha V of psi is T of alpha V. Now T of alpha V is the map from V hat to F, and that takes F to TV T of alpha V of F. This is same as F of alpha V. Now, F of alpha V, F is a homomorphism because this is an element of V hat. So this is same as alpha times F of V. Now, F of V is TVF. It's alpha TVF. And this is for every F in V hat. So that defines that T of alpha V is the map alpha TV. T of alpha V is alpha TV. Now this is true for every V in V and for every alpha in F. And what does it mean? That alpha V under psi is same as alpha times V under psi. So it preserves this scalar multiplication also. So what we have got that psi is a homomorphism. Psi is a homomorphism of V into V hat hat. You have to prove that this is 1 to 1 and this is also onto. In case of finite dimensional, one thing is enough, in fact. Now, psi is 1, 1. For 1 to 1, we prove that kernel is trivial. Kernel psi is 0. So what is there the kernel of this type? So recall that the kernel of a homomorphism is the set of all vectors in the domain which are mapped onto 0. So V psi is 0. This is same as all V in V, such that V psi, how did we define this V psi? This is TV. The map TV is 0. Now TV is 0 means what? That TV for every F is 0. F in V. Okay. Now what we have proved is that for a finite dimensional vector space, recall for a finite dimensional vector space over F and a non-zero and a vector is not 0 in V, there exists a linear functional f in V hat such that Fv is not 0. So this kernel consists of all such that TVF are 0 for every F, for everything. Now, so this has to be 0 since if V is not 0, then there would exist here an F in V hat such that this is F like this. So it's line. So V in V such that F of V is 0 for every F in V. So this has to be 0. What does the kernel consist of? Kernel consists of all V in V so that Fv is 0 for every V in V hat. So if there is a non-zero vector here in the kernel, then there will be a linear functional such that Fv is not 0. But then in the kernel only those vectors are there in V which are killed by every F in V hat. And that is the only vector 0. Because 0 under every homomorphism is 0. So what we have got is that the kernel is trivial. Kernel is trivial means the homomorphism has to be 1 to 1. And since V is finite dimensional and V hat also are finite dimensional, V double hat are also finite dimensional. So being 1 to 1 onto is implied. In fact, only one is necessary out of 1 to 1 onto. We get this psi is on, and hence what we have got V is isomorphic onto V hat hat. So we not only knew that they were going to be isomorphic, we now have obtained an isomorphism also of V onto V hat. And this mapping is psi. So we shall wind up here. Thank you very much for your kind attention.
Thank you, sir. Hello everyone. If anyone has any doubt from class lecture or from the reference book exercise, you have to solve the exercise given in the books that we professor has given as a reference. That is Ian Hastings topics in algebra and linear algebra by Hoffman and Kunje. So everyone have to solve the exercise questions from the books also. And please follow the book and for references might be some basic or easy thing professor will leave to you to read yourself. So please see the syllabus and follow accordingly book and class lecture. Anyone has any doubt or anything? No? Okay, thank you.